Out of all the animals on the planet, none are as feared as snakes. Their venom, responsible for claiming the lives of tens of thousands of people a year, has fueled the rise of these now extremely successful reptiles. Despite all this, their venom remains one of evolution's best kept secrets. Where did it come from? What is it made of? And why is it continuing to become stronger year after year? Today we'll go deep into the past, uncover the secrets of why snakes became venomous in the first place, and how this single adaptation triggered the greatest arms race in history. But first, we must travel back to the early Cretaceous, about 165 million years ago, when the earliest snake remains first appeared in the fossil record. Retaining small limbs, they more closely resembled their lizard ancestors than any living species. Since these early serpents lived underground, they had no need for limbs, and so they eventually lost them. This transition is thought to have occurred between 114 and 94 million years ago. Although this adaptation developed to assist a subterranean lifestyle, it would later allow them to thrive above the surface. But losing limbs was only the beginning. To dominate the animal kingdom, snakes needed one more critical adaptation. I think you can guess I'm talking about their venom, which catalyzed their rapid expansion during the Miocene. Despite evolving venom much earlier, it wasn't until some serious changes and a shift away from a mechanical hunting strategy that it became incredibly useful. While other animals had already evolved lethal venom, when snakes combined it with their other adaptations, they turned into killing machines. The elapids and colubrids, two of the most numerous snake families today, both spread out at this time, with the advent of venom allowing them to begin their reign of terror. One of the other key adaptations that helped them do so were grooved fangs. As seemingly the ultimate blueprint, they have evolved on 3 separate occasions. But what makes them so powerful? These fangs work by guiding the venom through a narrow canal, rapidly speeding it up, meaning the snake is able to inject more venom in a single bite. How these fangs evolved is pretty clear, but the evolutionary relationships between snakes are among the most convoluted of any group of animal. For the longest time, the evolutionary history of snakes was based exclusively on morphology, but since they often exhibit convergent evolution, this data led scientists in the wrong direction. And so at first, it was believed that venom appeared simultaneously across many branches of snakes and lizards. But when nuclear genomes were analyzed, something strange was found. The same proteins that snakes use to make venom were found in several branches of lizard, indicating that venom predates them all and evolved a single time around 170 million years ago. It was proposed that snakes must form a clade with the iguanomorphs and anguimorphs, which was later named Toxicophera. But once again, the paradigm shifted. The nuclear genome data, which the entire theory had been based on, was misinterpreted, and now the general consensus is that reptile venom evolved independently several times, with the majority of its diversification occurring in just a few highly venomous families after they had split off from each other. Having traced the origins of snakes and their venom, we now need to uncover how this deadly adaptation shaped the future of snake evolution. Ranking amongst the most complex substances in the world, some venoms consist of well over 100 different proteins, so it's clear that it can evolve rapidly. But this yet again is only a recent discovery. It was previously believed that snakes inject far more venom into their prey than is needed to kill them, meaning that their venom would not be subject to natural selection. Of course, this is not true and is easily disprovable. Within the pit viper genus, Cistrurus, there's a clear correlation between the potency of a snake's venom and the prey that it eats. Not just because it helps them catch more food, food, but because venom is extremely costly to produce. So the more potent it is, the less the snake needs to make for a fatal dose, meaning less of the animal's essential resources are used, providing great evidence of a strong selection pressure. But the overkill hypothesis might hold true for some groups of snake, such as the American moccasins, among whom a strong link between phylogenetic position and venom potency was found, hinting at a strong influence brought about by genetic drift and random mutations, as opposed to natural selection. But for groups where natural selection is a strong influence, an evolutionary arms race has unfolded for millions of years. As snakes increase the potency of their venom, their prey increases resistance to venom. Sort of like what happened during the Cold War, except this time the chain reaction that was brought about forever changed the planet's ecosystems. The most obvious battle is between wood rats and rattlesnakes. Competing in the same arena, wood rats are among the most common prey items for rattlesnakes, thus creating a very strong evolutionary pressure to develop resistance. Though unfortunately for the wood rats, it doesn't help them for long, as in response the rattlesnakes develop stronger venom, putting an even greater pressure on the wood rats in a positive feedback loop. This never-ending war isn't just between snakes and rodents. In the ocean, eels fight on the front lines. Their enemy? Sea snakes. But it goes a whole lot deeper than predator versus prey. Competition between snakes and their competitors also plays a significant role, not to mention competition between different snake species, further driving increases in venom toxicity. This never-ending battle is powered by an extraordinary genetic mechanism, and it all starts with an accidental gene duplication. On rare occasions, these duplicated genes are repurposed to create venom, giving the snake a higher chance of passing on its genes. This results in a relatively rapid evolution, allowing them to constantly refine their deadly serum. And the same way snakes are able to develop stronger venom over time, they can also lose it completely. In cases where a species switches to a different prey, the need for venom can suddenly diminish or disappear altogether. Marbled sea snakes, for example, have lost several of their ancestors' most crucial venom-enhancing genes, reducing its toxicity to 1% of its former levels. This is because, unlike its closest relatives, the marbled sea snake only eats fish eggs, rendering any venom it once had redundant. In Africa lives another egg-eating snake, the common egg-eater, and it too lost its venom. A common misconception is that animals can lose their adaptations if they simply no longer need them. In reality, adaptations are only lost if it decreases the animal's chance at survival. In the case of venom, the wasted energy expenditure is detrimental and allows for rapid evolution. This flexibility allows snakes to cover an extremely wide range of habitats and niches, as they can quickly adapt when faced with new challenges. But beyond genetic ingenuity and diet, several external factors play a pivotal role in shaping the evolution of snake venom. A study conducted in 2019 found two critical forces that influence venom toxicity, one of which is a larger body. At first you might think that it gives them more storage space and helps them take down larger prey, but the real reason is much more complicated. Due to having a larger body, larger snakes have a higher metabolic rate, meaning that producing the same venom takes up a smaller percentage of its energy, and so it isn't as nearly taxing as it would be to a smaller snake. The other major correlation was with the size of their ecological habitats, and you can probably guess why. Smaller habitats such as islands are usually closer to carrying capacity, increasing competition both within and between species, making stronger venom more beneficial. and in no species is this more apparent than in the golden lancehead, restricted to just a single small island. Originally, it was believed that the population numbered a whopping 430,000, although now it is estimated that 2,000 to 4,000 inhabit the island, which is still an incredibly high density of venomous snakes. Although appearing barren at first, the island is a major stopover for migratory birds, and so with no mammals present, the golden lanceheads had no choice but to specialize in birds, most importantly evolving an extremely fast-acting and powerful venom. In fact, it has a venom 5 times as powerful as its mainland ancestor, which is all the more impressive when considering how recently the golden lancehead evolved. Up until 12,000 years ago, the island which it lives on was still connected to the mainland, but when sea levels rose, it became separated. Whether the island was home to mammals in its early days is unknown, as it is quite possible that the snakes ate all of them, setting in motion a path to evolving extremely potent venom. All of this is to say that snakes evolved their venom for hunting, not defense. Or did they? Within the venom of certain coral snakes are toxins only capable of causing pain, an adaptation that wouldn't help with catching prey, although the best example of defensive venoms are those of the spitting cobras. These fascinating animals launch venom against possible attackers. Not only does it scare them away, but this venom is also adapted for causing pain. And our early hominin ancestors may be to blame, as when we became bipedal, we started to spend much more time on the ground, and so inevitably encountered far more venomous snakes. Adapting to this, our ancestors learned to throw rocks and sticks at them from a distance. Without any hands of their own, the spitting cobras had to find a different way. But compared to this frog, a venom-launching cobra seems pretty normal. Click this video to find out more.